Okay, here's something wild to think about. Every single Formula One car, right?
Yes.
It beams back over 1,000 different data streams every lap.
It's an incredible amount of information, truly.
But get it, just one tiny misread, maybe tire temperatures off by a degree, or the ERS deployment glitches, or oil pressure spikes unexpectedly,
Uh-huh.
and bam,
Wow.
what looked like a guaranteed podium finish can instantly become a retirement. Just like that.
It's probably the highest stakes IT system anywhere, really.
Yeah?
And that's what we're diving into today, this invisible army of sensors that honestly makes modern F1 even possible.
Exactly.
We want to get past the surface level stuff. Our promise to you is by the end of this, you'll understand not just what data they're grabbing, but how the engineers actually, weaponize it, how they use it for strategy. We're revealing secrets that, frankly, 99% of fans probably miss.
Yeah, this one's for you if you're already pretty deep into F1, maybe you're an engineering student, or just anyone curious about where science is really pushing the limits. We're skipping the 101 today. We're focusing purely on the deep tech, the machine minds, you could say, behind F1 engineering. So let's start with the car itself, the anatomy of speed.
Well, the sheer volume, like you said, over 1,000 channels, it's just staggering. And we're talking real-time microscopic analysis of everything the car is doing. It's not just, how fast it's going.
Right.
This system is designed to paint such a detailed picture that it can actually calculate things, metrics that you physically can't stick a sensor on to measure directly.
Wait, okay, hold on. You're saying it calculates things that aren't actually being measured by a sensor.
That's precisely. That huge amount of data isn't just for checking boxes. It feeds into really advanced models. So for example, you take data from the wheel speed sensors, combine it with suspension load cells, throw in the IMUs, that's inertial measurement units,
Okay.
and the system can crunch all that to figure out something like the estimated tire slip angle in real time. And that specific number, that's gold. It tells the driver, tells the strategy team exactly how close that tire is to losing grip.
Wow, okay, so you've got this beast crunching numbers. What are the inputs? If you've got 1,000 channels coming in, what happens if, say, 5% of that data is just noisy or wrong?
Yeah, that's the engineer's constant worry. It's why redundancy is absolutely critical.
So multiple sensors for the same thing.
Multiple types, yeah. You've got force sensors measuring aero load, pressure sensors for hydraulics, engine intake, and those IMUs are vital. They track every tiny movement, yaw, pitch, roll,
Why is it so critical?
because that's how the engineers know the exact moment the car starts to become unstable, often long before the driver can actually feel it starting to slip. So if one sensor reading looks off, the algorithm immediately flags it and checks it against related sensors. Like, is the brake pressure sensor data making sense compared to the temperature reading on the brake caliper? It's constantly cross-referencing. Then it's all filtered, beamed back through telemetry, and boom, it's on the screens at the pit wall instantly.
It's just amazing that these tiny little components, some are smaller than a coin, right? They're basically dictating strategy worth millions. How much did miniaturization and better wireless tech change things over, say, the last 20 years?
Oh, it was completely transformative, game-changing.
Yeah.
As sensors got smaller, lighter, and crucially more reliable wirelessly,
Yeah.
engineers could suddenly stick them in really critical spots that were just off limits before. Think like deep inside the suspension mechanism or right next to the ERS battery cells.
Getting data from the heart of the system.
Exactly. That granularity lets you monitor heat or airflow with pinpoint accuracy right where it's most turbulent and most important, like right at the edge of the floor.
And speaking of critical areas, the power unit, the PU,
Yeah.
that must be absolutely drowning in sensors, especially for heat management.
Absolutely. The PU it's an underappreciated art form in F1, honestly. These cars operate constantly on the very edge of melting down. Managing the heat in the brakes, the ERS battery, the PU itself, it's a perpetual balancing act. Too cool, you lose performance, especially on warm-up. Too hot,
That's a race over.
instant, catastrophic failure, retirement. So the sensors are feeding back temperature changes, the deltas, constantly. That allows tiny adjustments to engine maps, ERS deployment, even the physical cooling scoops, lap by lap, corner by corner.
Okay, so collecting the data is one massive challenge, but using it predictively,
Yeah.
that's where the real edge is, isn't it? If sudden overheating is the nightmare, what's the sort of slower creeping risk they're always trying to get ahead of?
That slow killer is degradation, specifically tire wear. And this is where the machine mind really goes to work. Raw numbers from force gauges or temperature probes, they're kind of useless on their own.
Needs context.
Exactly. They need to be fed into predictive models. Machine learning algorithms take all that real-time input, how fast the tire is wearing, how the temperature is spread across the surface, track conditions, and they build these incredibly sophisticated live models of tire degradation.
So is the algorithm just spotting when a tire is about to fail? Or is it more about optimizing performance based on, like, thousands of laps of old data? Is this real machine learning or just clever database lookups?
No, it's definitely the first one, and that's a really important distinction. It's true ML, part of what you might call the AI engineer's toolkit. It learns from historical data, sure, hundreds of races, simulations,
Right.
but the key is it applies deep learning to the live current sensor feedback. It's not just saying this happened last time. It's predicting the future state of that specific tire on that car right now based on its immediate heat and load. That's how engineers can forecast, with pretty high confidence, the exact lap a tire is likely to just fall off the cliff performance-wise.
Which tells them when to make that crucial pit stop call.
Precisely. It informs the strategy with data, not just gut feeling.
So when we hear those radio messages during a race, the engineers sound calm, but the words are often cryptic. They might be masking much bigger issues or acting on these predictions.
Absolutely. They're speaking in code a lot of the time. It's the engineering language, driven by telemetry. An engineer might say something like, okay, we need to box seeing a delta on compound 3. Sounds pretty bland, right?
Yeah, fake.
But it's shorthand. It could mean, okay, the tire temp probes show we're accelerating 5% faster than the model predicted. If we stay out, we risk losing 4 seconds a lap very soon. We need to pit now for an aggressive undercut. They're decoding and solving potential crises in real time.
That's fascinating. And it sets us up perfectly for a real-world example.
Yeah.
Where did this kind of sensor-driven insight directly lead to a win? Let's talk Singapore 2023.
Singapore 23. Yes, that's a perfect case study. High pressure, incredibly close race. It all came down to strategy timing, really. And the critical factor was the data streaming back from the tire temperature and pressure sensors.
What do they show?
Well, the sensors indicated that a specific tire compound on a rival car, it was either holding on to heat differently or degrading just slightly faster than expected, maybe faster than the rival team's own model predicted. This opened up a very narrow window for an earlier than expected pit stop, the undercut.
But just relying on sensor data for such an aggressive move, isn't that incredibly risky? Surely there's a human judgment call in there too.
Oh, always. The data gives you the confidence, the quantification of the risk versus the potential reward. But the human makes the final call.
Okay.
What the sensor data did was show Ferrari exactly when their rivals' tires were likely at their weakest point. It created this tiny window of opportunity, maybe only a lap or two wide. Without that hard data, that objective evidence,
It's just a gamble.
it's a blind gamble. Instead, it was a calculated risk backed by the machine intelligence. And while it worked, they took the lead right after the stop.
And I suppose that rapid response, driven by data, is behind those engineering war stories. You sometimes hear teams fixing things mid-race.
Absolutely. The whole engineering culture is built around sensor flags a problem, you react immediately. Sometimes it's slapping on some emergency tape to fix unexpected drag from minor damage. Other times it's reprogramming hybrid system settings right there in the garage during a stop. It all hinges on getting that immediate feedback from the sensors. If a sensor says the car's floor isn't producing the downforce it should, or something is dangerously
I
stretched,
had to figure out a workaround fast.
in minutes, sometimes even while the car is still circulating, that data guides their frantic decision-making.
It's incredible how this tech saves races minute by minute. But the bigger impact, the stuff F1 develops, often shows up years later elsewhere, doesn't it? Let's talk about that ripple effect. Where does all this sensor discipline filter out into the world?
Yeah, F1 is basically this hyperspeed R&D lab for sensors that have to survive incredible stress continuously. The methods, the discipline developed there, it's a powerful source of innovation. You see it filtering directly into high-performance road cars now. Think about advanced thermal management in electric vehicles, keeping batteries happy, or much smarter traction control systems that don't just react to slip but predict it using sensor fusion. It also influences aerospace, designing for efficiency and monitoring structural loads, and even, believe it or not, consumer health wearables.
Really?
Wearables. Sure. That idea of continuous, multi-point biometric monitoring, it shares a lot of DNA with F1's need for constant, detailed telemetry from the car and sometimes even the driver.
Now, you mentioned a couple of big moon landing moments in recent F1 tech. What's the first one that's really shaking up design right now?
The first, I'd say, is the big aerodynamic shift that started in 2022. Going back to ground effect cars, it's completely changed the design philosophy. Teams are now chasing performance gains in these microscopic details of how air flows under the car.
Right, the floor is everything now.
Exactly. Intense focus on tiny tweaks to the floor edges, managing the vortices there. And that's only possible because they can now embed sensors right along the floor edge in the diffuser places, giving them unprecedented real-world data on air pressure under the car. Not just what the wind tunnel or CFD predicted.
And the second big one, maybe the one with even broader long-term implications.
That has to be the hybridization of the power units. These current V6 turbo hybrids, with their complex energy recovery systems, the ERS, they are arguably the real moon landing of modern F1 tech.
Because they're so complex.
It's unbelievably complex. Managing the heat, the energy flow between the combustion engine, the turbos, the batteries, the electric motors, it requires an insane amount of data processing and sensor integration just to make it work, let alone be competitive. The lessons F1 is learning about power density, rejecting heat efficiently, delivering instant electric torque. That's invaluable knowledge for the entire auto industry as it moves towards electrification.
Okay, that leads us nicely into our hidden bonus section, something happening behind the curtain. When you have data this valuable, it naturally becomes a target. Let's touch on the cyber war, the fight for IP.
Oh, it's a constant silent battlefield. Teams invest heavily in cybersecurity because the stakes are so high. They're defending complex CAD drawings, critical wind tunnel data, CFD results, and they're constantly fighting off hacking attempts. It's relentless.
Where's the biggest vulnerability?
Often it's in the performance metrics themselves, the secret sauce, the specific engine map tuning for a track, the optimal aero balance settings. That's the crown jewels they guard most fiercely.
And we hear whispers about teams using things like steganography. Actually hiding data within other data.
Yeah, steganography is basically the art of hiding a message or file within something else that looks innocent. In F1, it's not just about hiding a file, it's about making crucial performance data almost impossible to distinguish from background noise if someone does manage to intercept it.
How would they even do that?
Well, they might embed key metrics like, say, optimal engine timing advance, or how much the floor is flexing in a specific corner within what looks like routine system telemetry. Or maybe even encode it in tiny, almost invisible variations in the car's visual livery design files. The goal is to frustrate anyone trying to reverse engineer their advantage. If a rival scans their car or intercepts data, but they can't tell the signal from the noise...
They can't copy it effectively.
Exactly. It's another layer of defense in what's fundamentally a zero-sum game of information warfare.
So pulling this all together, what's the big takeaway for us watching the race? It seems like modern F1 is maybe less about just the driver in the seat and much more about this incredibly complex data cockpit. It's where human skill meets machine intelligence.
That sums it up perfectly, and it raises a really interesting question for you to think about next time you're watching. Teams obviously rely heavily on scanning rivals, analyzing data streams, basically reverse engineering each other's cars to find an edge.
Yeah, it's standard practice.
But where do you draw the line? Legally, ethically? Where does competitive inspiration cross over into outright copycatting or IP theft? That battle isn't just fought on the track anymore. It's fought deep in the data streams.
A fascinating gray area, for sure. And it highlights the pressure. If one bad sensor reading can end your race, imagine the pressure cooker environment of the pit stop itself.
Oh, yeah.
Next time, we're going deep on that. We'll do a slow-motion breakdown of pit stop optimization. We're talking pure human precision, the mechanical choreography, the incredible microengineering of the tools they use, all to shave off milliseconds. You seriously won't believe the complexity behind getting that stop done in under 2 seconds. You definitely don't want to miss it.